the cosmology course. So last time, so this is our periodic table of elements, approximately. And so last time we were wondering when and where these elements could have been produced in our universe. So at large, so if you average over all space, basically most of the universe is formed by hydrogen, 75% by mass. And then you have the second one is 25% is the helium, and the rest is just only a little bit, a little seasoning, which we have. But of course, that's interesting seasoning. But you know, basically this forms 100% of the universe. So now what I showed you last time as well is that this one-line calculation is that there's this theory that you can fuse heavier elements, for example, helium, in the center of the star. But the problem is that this releases quite a lot of energy. And so if you were to fuse 25% of helium in stars, your sky would be very, very bright. So there would be so much energy released that we wouldn't have a dark sky. But of course, we don't observe that. And if you do the calculation, you find that only less than 1% of those 25% of helium could have been fused in stars. So now, let's us do this back-of-the-envelope calculation. And the aim of this calculation, I'll be cheating a lot. But the aim is to show you that Big Bang nucleosynthesis actually gives the right ballpark for these 25%. Okay, so that's the aim of the first half of this lecture. So let's return back to a temperature which is few MeV. And then the statement is that at this temperature, it's the weak interactions which become quite inefficient to maintain all possible equilibria you can imagine. So weak interactions become inefficient. And it has, very many consequences. So the first consequence is that the neutrinos actually decouple from the rest of the plasma. So neutrino decoupling. So neutrinos are coupled to your thermal bars through these weak interactions. And so you have interactions like neutrino plus antineutrino, and it gives you electron and positron, or electron plus neutrino gives you the same thing. So there's just a scattering, and the same for other things. So this is just an example of two interactions you can have. So now you need to estimate what is the rate of this interaction. And so let's do a very rough approximation. So we are at temperatures which are roughly MeV. So at that point, you don't really have to care about that you have weak interactions. You can equally well do with the Fermi theory. Okay, so weak force at these temperatures is well approximated by the Fermi theory. And the Fermi theory is characterized by the Fermi constant, which is dimension full constant, which of course is a problem for normalization, but for us it's quite convenient. So G of Fermi is, well, you have two interactions of the intermediate things. So that's why you have G square, where G is the coupling of the weak theory. And then let's say you have the mass of W square in the non-relativistic approximation. And if you calculate this guy, it's 10 to the minus 5 GeV to minus 2. Okay, so that's the strength of the coupling in Fermi theory. Okay, so now we want to estimate what is the reaction rate for these interactions. And so very, very approximately, if you look at all these particles here, they are all relativistic, right? So the only thing which has the right units of energy is the temperature here. So all the masses I can neglect, all the chemical potentials I can neglect. So approximately the only thing I have here is the temperature. Okay, so from here it follows that if I want the interaction rate for this thing, which is 1 over time, has units 1 over time, so it has units of energy. Okay, so now the interaction rate is like an amplitude square, so I'll have to have GF square, which gives me 1 over energy to the 4. And so the only thing which has units of energy is the temperature, and to have at the end something which has units of energy must be T to the 5. Okay, so that's an approximate estimate for the reaction rate of these interactions. Well, everything is relativistic, right? So, yeah. So electron mass is half MeV or something like that. So it's still relativistic, right? So, yeah, you're right. You can do, you can do much better approximations, but this is enough. I'll be cheating anyway. I'll be cheating a lot in this calculation. So this is our reaction rate, and so now you want to compare this to the Hubble rate, right? So compare to Hubble rate. So you have your Friedmann equation. H squared is 8 pi g Newton over 3 rho minus k over a squared. Okay, so that's your Friedmann equation. So now we are in radiation-dominated era. So the curvature doesn't really contribute, so I can forget about this term. And let me use units. Well, let's just say that g Newton. So, okay. So g Newton is just 1 over m Planck square. Later on, I will say that 8 pi g Newton over 3 is 1 over m Planck square, so it'll be different by 8 pi over 3, but doesn't matter. So at this point, it's just g Newton is 1 over m Planck square. And then you can use what rho is in terms of our thermodynamic formulas. So at a given temperature, I can calculate rho, and that's what we have estimated in past 2 lectures. So this is equal to 8 pi over 3. And then the formula for rho is just pi square over 30 g star, and then T to the 4. And then I still have this g Newton there, which gives me 1 over m Planck square. Okay, so that's formula for H square, which means that if I want to compare when this is true, then you have that GF square, and that happens for some temperature. That's that's temperature by T star. So GF square T star to the power 5 is approximately equal to. Now I have to take square root of this thing here, right? So it will be some number like given by the square root of these guys, and then it will be T star square over m Planck. Okay, and it'll be that number, which actually, if you plug in, so you calculate all these things in. So this gives you that T star is approximately 1 MeV. And here I use that G star, which is the number of relativistic particles at that temperature, is approximately 10. So you calculate electrons and you calculate neutrinos and all these things and how many of them, how many degrees of freedom I have which contribute to my plasma. Okay, so you can estimate that really neutrinos decouple from the rest of the path at approximately this T star, which is 1 MeV. Okay, very, very rough estimate. And you will play this a little bit more in your tutorial and do it a little bit more exactly. You will reproduce this calculation and do something more and do it more exactly. But this is approximately what it is. Okay, so that's one thing which happened. So neutrinos decoupled from thermal equilibrium, but also neutrinos coupled to my protons and neutrons, and they sort of keep a balance, chemical balance between protons and neutrons. So that's the second thing. So second thing that happened is that chemical decoupling covariance so you have nuclear reactions like proton likes to eat electron and produces a neutron. And neutrinos play a key role in these interactions. Or you can have that proton just decays into neutron plus neutrino plus positron, and so on. So you have these types of interactions. So you see that neutrinos play an essential role in these interactions. But basically, they maintain the balance between protons and neutrons. Okay. So now when these reactions cease to work properly, then actually protons and neutrons will separate from each other. Okay. So when they cease to be efficient, then neutrons freeze out. If no longer efficient. Okay, so now you can spend a lot of time estimating at which temperature this happens. It happens for a temperature which is lower than this T star here. And the calculation is quite complicated, but the result is basically the same as T star. So let me estimate this guy. And here I'm just giving you a result, which is adjusted so that it works. Okay, so this happens at T star, which is 0.8 MeV. So then, actually, neutrons decouple from protons. Okay, so I'm just giving you this. But there's no much time difference between this guy and that guy. So once neutrinos decouple from thermal baths, they sort of cease to be efficient also in these types of interactions. Okay, so now at the freeze out, of course, the abundance of protons and neutrons is governed by their mass, and it's according just to the Boltzmann law, right? So the number of neutrons divided by the number of protons is just governed by the Boltzmann law, which is Q over T star. T star is the temperature, and then Q is just mass of the neutron minus mass of the proton, which is 1.3 MeV. Okay, so it's just the difference between the masses of neutrons and protons, which basically causes the fact that you have many less neutrons than you have protons. So this is, if you plug it in, and you use 0.8 MeV, then you get 1 over 6. So number density of neutron is 1 over 6 number density of protons at that point. Okay, just thermodynamic equilibrium here. Okay, so very good. So the neutrons freeze out, and at that point we have that many of them, and compared to the protons. So what happens next is that you have to start fusing these heavy elements. Okay, but the problem is that the helium is not fused immediately. So it consists of 4 baryons. You have 2 neutrons and 2 protons. So you would have something like 4 particle interactions. But of course, these are very rare, and the cross-section for 4 particle interactions is very low. So what you rather do is that you fuse some lighter elements, for example, deuterium first, and then like in 2 particle interactions, and then again you smash deuterium and form finally helium. So there is some time before actually enough deuterium is formed, so then you can start forming helium. Okay, so in that time, if you want, neutrons just sit there and wait. Okay, so neutrons decay because they are unstable. So according to that reaction, so a neutron just goes to a proton plus electron plus this guy here, because simply proton is better than neutron. So according to the decay rate, so you have how much you wait, and this is the lifetime of the neutron. So now lifetime of the neutron is something like 15 minutes. And the truth is that before the helium finally starts to be produced from these lighter elements like deuterium, it takes 3 minutes. So T can be approximated like 3 minutes. So that long you have to wait until it finally starts fusing helium. Okay, so that of course, means that I significantly decay some of the neutrons. So this fraction 1/6 actually goes to something like 1/7. Okay, so this decay causes that now the ratio is approximately 1/7 instead of 1/6. And then all neutrons eaten by helium. Okay, so if you see that if I had, if I shuffle these numbers, and for example, this guy wouldn't be 15 minutes, but would be only 10 minutes, then we wouldn't have any helium at all, because all neutrons would decay, and we couldn't form helium, right? So anyway, so it's very, very important what these numbers are in this calculation. So anyway, so we have 1/7. And okay, let's just say that the delay, why you have to wait those 3 minutes, is related to so-called deuterium bottleneck. Basically, you have to wait until enough deuterium is formed, and you can start fusing helium. And then this is actually suppressed, which is suppressed and I'm not going to show that, but which is suppressed by this eta factor, which is the number of baryons divided by number of photons, which is something like 10 to the minus 9. So that means that basically the cross-section, well, the interaction rate of these before you form the deuterium is proportional to eta, and so this is really, really small. So that's why you have to wait a lot, and that's why you wait 3 minutes. But this eta factor really enters this nucleosynthesis, and if you start playing with this eta, then you get completely different results. And I'll show you in your handouts that. Okay, so we have number of neutrons divided by number of protons, approximately 1/7. So now helium, of course, is 2 neutrons plus 2 protons. that means that total mass in helium is 4 times. For this calculation, you can treat the mass of the proton equal to the mass of the neutron, 4 times mass of the proton, times, well, number density of neutrons by 2, because each helium has 2 neutrons. Okay. Okay, so we get that the fraction of the mass of the helium divided by the total mass of the baryons is, well, this is 2 MP and N, and this is MP NN plus NP. Okay, if you plug in the numbers, you get this is 2 plus 1 plus 7 coming from that 1 over 7, which is precisely 1 over 4. So you form 25% of helium. So this calculation is really tuned so that it gives you exactly what you need to get. But approximately, you know, this is true approximately. So of course, you can do much more complicated calculation, and you can do it in kinetic theory and include all the possible reactions, but the result is the same. Okay, maybe. That's the density, so yeah. So it's yeah, thanks. But this the fraction is okay. Yeah, but thanks. Yeah, you're right. Absolutely right. So you know, this calculation shows you that really maybe the Big Bang nucleosynthesis is not such a stupid idea. It's definitely a better idea than the helium the helium was formed in the center of massive stars. So notice also that, you know, this calculation. So no matter. So we skipped many steps, and we did, you know, very, very approximately, but it's obvious that this calculation depends on lots of parameters which enter standard model, right? So it depends on the decay time of neutrons. It depends on the masses of protons and neutrons. It depends, crucially, on this parameter eta, as you will see in your handout, and so on. So in some sense, BBN provides you know, a real test of fundamental physics. Right? So BBN is a test of fundamental physics. Similar to Large Hadron Collider, right? So if you, you know, start producing some new theories which go beyond standard model, so if you predict some new physics, you better check it, but it still gives you the right prediction for BBN, because if it doesn't, then you are on a wrong track, right? So it really, you know, imposes severe restrictions on what you can do. And so here we tested, you know, G star. So that's something which enters that calculation. So it's how many particles actually were relativistic at the time. So if you start producing new particles in your theory, then of course G star will change, and that estimate will go differently. You know, tau n, eta, G Newton, G Fermi, and, you know, all these things actually enter this calculation. And once you start messing with these things, you better be careful what you are doing. Okay, so now if you look at your handouts, then so let's see if it works now. Maybe. So basically the first picture, which we still don't see, shows how this calculation went. So you start from an equilibrium situation, and so neutrons, the number density of neutrons is governed. It's gone. So here's the fractional abundance of of elements, and here's the temperature or time when this happens. So, you know, for high temperatures, you have equilibrium maintained by all these interactions, chemical equilibrium between neutrons and protons. At that point, when these interactions changing neutrons to protons actually cease to be efficient, neutrons freeze out. And so instead of following an equilibrium curve, which would be this curve here, you rather freeze out at this point. So it seems like you want to freeze out, but actually because the neutron is unstable, it starts decaying. So that's why so this would be like a freeze out value, but neutron starts to slightly decay from this 1/6 to 1/7. So in the meantime, the deuterium is actually formed. And so I said you have to wait some time, which is suppressed by this parameter eta, until a sufficient number of deuterium is formed. And then deuterium participates in fusing helium. So basically, you kill most of the deuterium by fusing the helium here. And so this is the remaining value of the helium, and this is the remaining value of the deuterium. Okay, so this is the picture which basically displays this calculation as we have done it. Okay, so now this picture is quite interesting. It displays, so here is this parameter eta times 10 to the 10. And here's the abundance of various elements. So now the gray things, so this thing and that thing, for example, or this thing is just the observational bound. So which tells you that eta has to have this value. Okay, so this is an observational bound. This is also an observational bound. So the the blue region, red region, and this region is just the theoretically predicted value. So if you start messing with eta, this is the theoretical prediction for how much helium you should have. And you see that the observational thing, which meets roughly here, fix your eta and fix how much helium is produced, and so this is really it's an agreement. So okay, so if you want, this is just to fix eta. For deuterium, this is a prediction already, right? So this is my theoretical curve. I fix eta, so do I really see what I have predicted? Okay, so for deuterium, it works very nicely. For lithium, however, if you look at this guy, so you should be somewhere here, but the theoretical prediction is this one here. So everything else but the lithium agrees pretty well, but lithium is off by a factor of 3. So the question is, is the observation wrong or is the theory wrong? Something for you, an essay project, right? So people don't know. So many people think it's actually the observation is wrong, that you cannot really detect lithium properly, in distant galaxies and so on. But no. helium-3 doesn't have, WMAP, fix your eta. But you always want to be, at a cross-section of this eta and other observational constraints. So this is my observational constraint for helium. This is my observational constraint for deuterium, but there is no observational constraint for helium-3. So this one is standing because you don't have observational constraint, but here you have, and it's off. So problem for you, can you actually find what's happening with lithium? And finally, this is if you're interested, oh no, so this is just only these 3 elements. And then if you want to read about the explanation why, if you change eta, what happens with the theoretical prediction is here. But you see that really I have to eat deuterium, all the deuterium is basically captured by helium and only a little bit is left. The same with lithium and so on. Right? So these are, this is really a fundamental physics which you have to, these are constraints on fundamental physics. So no matter which theory you come with, you have to basically predict the right things. So maybe if your theory can predict the same thing for deuterium and helium and can predict for lithium, then your theory is better than the standard model. Okay, so questions? So if there are no questions, let me start part T, and that's CMB. And I'll return to CMB later on this week, but just to give you a first flavor. So now we've been at temperatures MeV, so now let's go to even much lower temperatures, which are roughly T, like electron volts. And then at these temperatures, you have plasma. It's my slice of plasma, and so you have electrons there, and you have gamma particles, and then you have your fused helium, and then you have hydrogen, and lots of gammas and lots of electrons. Okay, so this is how your plasma looks like. And all massive particles, including electrons, are already non-relativistic. Particles, non-relativistic. Aha, interesting. Can you? Oh no. Okay, we can continue on that part of the blackboard. So now the first thing which happens at these temperatures is that the helium captures the electrons and becomes neutral. Okay, so first what happens is the recombination I have not much to say about these things. I just want to tell you what needs to happen first and what happens second and so on. So it happens in 2 steps. So helium 2 plus first captures 1 electron, and then the rest captures the other electron. Okay, so it happens in 2 steps. So anybody knows why helium becomes neutral before the hydrogen becomes neutral? What do you think? Because the ionization potential is bigger than for hydrogen. So larger ionization potential. Okay, so at this point, I've captured some electrons, but I still have my plasma is still not neutral. I still have hydrogen plus and electrons and all these things. So still, the photons cannot roam free. They are still captured and they still participate various interactions. So universe is still opaque. Because photons still cannot roam free here. But the fact that helium is now neutral has effect on the speed of sound of propagation in your plasma, and that actually affects CMB. Which we'll discuss today and tomorrow, the CMB picture will be altered if we didn't have helium in the plasma. So this thing actually has effect on that CMB. Okay, and this happens approximately at T, which is like 5,000 Kelvin. Okay. So then the second step which happens is that of recombination of hydrogen. So of course I have proton plus electron, hydrogen plus gamma. This is what happens. So this is not an equilibrium process. You have to use kinetic theory. but you will calculate it in your homework too by using equilibrium Saha approximation. So need kinetic theory. So this is like warning you that your homework will not give the right results, but almost right results. But qualitative results can be obtained by equilibrium thermodynamics. And in this case, this is called Saha approximation. So the guy was called Saha approximation. And this will be studied in your homework too. So let me just give you the result, what you should get. So people like to introduce a fraction, ionization fraction. Which is number of free electrons, or density of free electrons, divided by density of baryons. So these guys are free electrons. Okay, and so now you have some thermodynamic formulas and so on, and you will do it yourself in your homework too. But if you, well, you have to take something as an indication that now actually, most of the electrons were already combined with my protons and formed the neutral hydrogen. And so let's take this when Xe is something like 0.1. So if you have 10 times more baryons than you have now free electrons, then you say, well, the recombination already occurred. Okay, so this happens for T recombination 0.3 eV, which is something like 3,600 Kelvin, and happened at the redshift, which is 1,300. Okay, so this is the result of your homework, if you want. So, but you have to, say, well, this I consider that a combination already occurred, and this is the result which you get. So interestingly, so now at this point, all the electrons, well, most of the electrons are already captured by helium and hydrogen, but there's still only a little bit electrons left. But electrons or photons like to bump into electrons, right? So they really, if they can find one free electron, they just bump into it. So that's why even after the recombination of hydrogen, still universe, you cannot see through universe because still, there's these crazy interactions. So the last step is the photon decoupling. So at this point, most free electrons already eaten. But the remaining free electrons actually bump into photons like crazy. So still, photons bump to remaining free electrons like crazy. That's very important, like crazy. And the process is called Thomson scattering. So this is Thomson scattering. Okay. So basically what happens is that you have an electron and a photon bumps into it and forms an electron and a photon. So basically the photon is absorbed for some time and then it's radiated away again, and so on. So you need to seize these interactions, and only after the reaction rate actually, of these interactions is very, very low, finally the universe is you can see through that universe. So there's H, which depends on temperature, and you can do exactly the same calculation. You can compare gamma of this interaction, and you can compare the Hubble expansion rate, and that gives you T decoupling. And so this T decoupling is 0.27 eV, or 3,300 Kelvin, and happens at Z, which is 1100. And if you are still interested in this ionization fraction, then it's now 0.01. And again, you will estimate these things in your homework. So basically, you have this plasma, and where you have some electrons here, still some free electrons, and the photons, they just go and bump like crazy into these things. But suddenly, at this temperature, this reaction doesn't go anymore, and then the photons actually roam free. So this is 3,300 Kelvin, and then after these photons roam free, and in fact only 10% of these photons actually found somebody to scatter with after this decoupling time. So most of them, they have never scattered anybody else. So they just really roam free, and then you basically have a picture of the time when this happened. This happened very suddenly, and the surface when it happened is called surface of last scattering. Okay, so this guy is called surface of last scattering. So photons like to scatter if they can, and so they were trying to do it until they could, and then when this wasn't efficient anymore, they just go and never scatter again. Okay, so now of course what happens to these photons, because they roam free, is that they basically move on geodesics, on light-like geodesics, and as they move, they lose their energy because they are redshifted. And at this point, you observe them as the CMB, which now has, so here you observe T0, which is something like 3 Kelvin. So that's the remaining temperature of this 3,300 Kelvin things when this happened at redshift 1100. So now the photons have approximately 3 Kelvins. Okay, and this is CMB, cosmic microwave background radiation. Questions? We still have 10 minutes. It's amazing. Okay. So now these photons, well, first of all, observation of these photons in the 70s was last nail in the coffin for steady state theories, right? So this is something which was really predicted by Big Bang theory, and not the movie, but the real Big Bang theory. And the observation that really we observe these photons coming from all possible directions at approximately this 3 Kelvin, which was, by the way, predicted by Gamow. It should be like 3 Kelvin, was like amazing support for Big Bang theory rather than the steady state theory. Well, nowadays, the CMB radiation is actually the biggest source of what we know about the universe. And one thing you can look at is the CMB spectrum. And what you will find is this beautiful thing. So it's an intensity here, and these would be the measurements, and this is the frequency. Frequency is measured in 3 times 10 to the 10 hertz. Okay, and so these are the measurements. And of course, you can connect these measurements as a right theoretician. Okay, and you know, if you do that, you find that this is exactly the black body curve. And so this is a perfect black body. Or Planck spectrum. So it tells you that actually when the radiation was released, then your plasma was in perfect thermodynamic equilibrium. So, you know, just before the surface of last scattering, you know, everything was in perfect equilibrium, and then suddenly, you know, like you remove the wall, and the photons go to you, and so emitted by plasma in thermodynamic equilibrium. And this is the Planck formula, which you can fit in. 2h nu cube c square 1 over a h nu kt minus 1. So you can fit in this guy. So now what is very interesting is that if you look at each direction in the sky, you see this perfect black body spectrum. But the truth is that each direction has slightly different temperature. Okay, so each direction, slightly different temperature. So if you average over these temperatures, then these 3 kelvins is actually 2.7. So this is your average over all possible directions. But you see the fluctuations, delta t, which is like really what I measure in that direction minus the average one. And the fluctuations are of the order 10 to the minus 5. If I look at that direction, it has slightly different temperature than that direction, slightly different direction, temperature than that direction, and so on. Okay. So now what people like to do is that they like to plot these things, you know, on the sky. So you can multiple moments. So basically, you can plot these things on the surface of the beach ball, right? And so what I am displaying here is delta t, and you'll see that, you know, there's some average which is subtracted, and then, you know, some spots are hotter, some spots are colder, and so on. So you see, you know, something like this. So these tiny fluctuations. So this is our beach ball. And you can actually buy these things on a beach ball. Okay. And so, because it's on S2, it's natural to expand these fluctuations in spherical harmonics, right? So expand in spherical harmonics. because we are on S2. So we have the delta t theta and phi. So now there are these L and M's, which you know from quantum mechanics. So L goes from 0 to infinity, total angular momentum, and then the projection M goes from minus L to plus L, and you have your coefficient of the expansion and your basic function. So you are doing something like a Fourier series, Fourier transformation, but you are choosing different bases. You are not choosing e to the kx, but you are choosing this basis, theta and phi. Okay. So people like to expand these things in spherical harmonics. Then by measuring these points, these tiny fluctuations here, what you really measure is these coefficients of expansion, right? So now it's obvious that if I fix L, then M can still go from minus L to plus L. So for fix L, I have 2L plus 1 ALMs. So if you fix L, then you have 2L plus 1 ALMs. So now what is also an interesting information is that you may be interested, so let's say I fix L. So, to what distance it corresponds on the sky. And there's a beautiful formula that the angle on the sky is something like pi over L. So if I fix L 200, then it corresponds to 1 degree on the sky. Okay, so on the sky, angle on the sky. So for small l, this is like huge distances. It's like huge correlations in the sky, if you want. Okay. Yes?
What is that angle?
Angle. Did I spell it correctly? It's really, if I fix L, what are the distances I'm talking about in the sky? So if I take L equal to 1, right? So then I have like 180 degrees divided by 1. So I'm talking about correlations between this guy and that guy. If I take L 200, I'm talking about correlations which are separated by 1 degree on the sky. This is the angle on the sky. This is an approximate formula. It's not.
Is this an opening angle or is it a solid angle?
Very good. What is the difference? I don't know. Huh?
In linear direction, there's like a length scale, and the other would give you like some kind of an area. So.
It must be.
I mean, that probably doesn't really matter. But
Yeah, probably the area, I'd say. Okay. So once you do these things, then what people really draw is the power spectrum. CL. And so what you basically, so you measure these ALMs for our universe, but for fixed L you have, 2L plus 1 ALMs. And so really the M doesn't matter because the M tells you how you rotate your sky. So if you want something which is invariant under rotation of the sky, then you rather construct a length in this M space. And that's done here. So observation, what people like to plot is CL is the power spectrum, and it's defined by 2L plus 1 sum over M, and is the sum over ALM squared. So that's what is called a power spectrum, CL. And if you want, it's a length of a vector in M space. So why this is interesting is that because the length of the vector in M space is rotationally invariant. Okay, it does not change. So basically, the M measures like angular momentum in the z direction or whatever. So you are preferring z direction. If you want something which is invariant on what you choose, how you choose your axis, then you rather talk about the length of the vector in this M space, and this is the quantity you consider. And so if you plot this guy, so L is here, and then CL is here, and you get this beautiful picture. This is called, well, it's the power spectrum here. So this is like 2, this is like 50, it's like 500, and so on. And so the measurements are all on this curve. So this is like a theoretically predicted curve, which you will not predict, but I will tell you how to predict it. And the observations, in this part of the exactly on that line. So observations will be like sitting on that theoretically predicted line up to the point where L is very, very small. And then the observations have large error bars, if you want, and the theoretical prediction also has, okay. So there are some large errors for small l, but other than that, everything fits perfectly to theory. Okay, and what is amazing is that you can fit this, you can predict this theoretical curve by 6 parameters, and I'll discuss what they are next week. But basically, to predict this curve theoretically, all you need is 6 parameters, and then it agrees perfectly with the observation up to small l. So let's see if it works now. It doesn't. Okay. Oh, it does. Very good. So just to show you what I just told you, maybe. Okay, so here is, so the green thing is the perfect black body, and the red crosses is the observation, which was produced by Kobe satellite. So you see that really in each direction I have perfect black body. In fact, this was a little bit more complicated, is that when first CMB was noticed, it was actually on this steeping, well, on this part of the curve, and you could observe, on a little tiny region over here, and that was the discovery, because everything what is up here is actually shielded by atmosphere. So actually you cannot see the spectrum over here because atmosphere prevents you. So you need a satellite. That's why the Kobe satellite was actually sent up there and measured all these points here. But from Earth you basically get this part, and it was done by Wilson and these people, and they got a Nobel Prize for that. And it was all discovered by mistake, of course. So now this is the ball, the beach ball I was talking about, and as the latest measurement by Planck. So really, you know, it goes from 200 microkelvin to plus 200 microkelvin. So it's really, and what is subtracted is this 2.7 Kelvin, right? So it's really teeny fluctuations, but it's the most, you know, accurate map of this CMP fluctuations, if you want. So now here is the comparison. This will be very bad quality, but anyway. So how it evolved. So this is copy in 92, and then WMAP got a little bit better, and now we have perfect resolution, this Planck in 2013 of this thing. So now here's the CMB thing. So again, notice the large error bars for small l. But here, at this point, you know, it all agrees with the theory very well. So here you have some problems, but okay. So this is the CL power spectrum, very beautiful thing. It tells you everything about the universe, basically. Okay, and here is a joke to finish with. So how people can understand scientific talks. So here you think you have understood something, right? But then you realize you haven't understood anything, so you are very confused, right? And then maybe there's some interesting points, and you know, too many details, and then you are looking for coffee or something like that. So this is how CMP spectrum precisely maps what's happening with speakers in scientific talks. Okay, so tomorrow we shall start dark matter. Thank you.